Okay, hello students. This is section 5. I encourage you to watch section 1, 2, 3, and 4 before watching this one. So let's go ahead. That 360 degrees is equal to 2 pi in radian. Okay, so alright, so this is a circular path. Here's the center. If an object at this point, A, moves from this point to this point, B, alright, the angle swept through to be theta, that's angular displacement, and then this arc, let's call it S. Alright, now if we are to take the ratio of S to the rest of the circumference, that would be S over 2 pi r equals, then we take the ratio of theta, alright, to the rest of the angle in a circle, so theta all over 360 degrees. Okay, now we know that once r becomes equal to S, then theta will be equal to 1 rad. By definition, 1 rad. Alright, you have 1 rad when r is equal to S. Okay, so if we plug this in, we are going to have S over 2 pi r, but then I want to cancel the S now. Cancel this S and put r is equal to, now instead of writing theta, let me still go ahead and write it. Alright, and cancel it and put 1 rad all over 360 degrees. Okay, so r takes care of r here, and then we are left with what? 1 all over 2 pi is equal to 1 rad all over 360 degrees. If you work this out, to become clear that 2 pi rad is equal to 360 degrees, and that is it. Alright, so number 2, show that the relationship between linear speed and angular speed is given by v is equal to omega r. Okay, so this is my circular path, is the center. If an object moves from this point to this point, an angle will be swept through, that is theta, and then this distance here, AB, let me call it what? S. Let me call it S. Okay, now by definition, we know that theta is equal to S over r, which is the radius. Let's call this equation 1. And I also know by definition that v is equal to S over t. That's the linear displacement or distance over time. And then by definition, omega is equal to angular displacement all over time. Let me call it equation 3. Okay, so if we, from equation 1, let's get that S is equal to theta times r. Let's call it equation 4. Alright, so put equation 4 into 2, then we are going to have v is equal to, instead of S, we'll plug in theta times r, then all over t. Now recognize that this is our omega. Alright, so v becomes what? Omega r. Okay, so that is it. Another way would be for us to recall. This will be the second method. Just recall that S is equal to theta times R. Remember, from this, all right? And then we now divide both sides by T. Divide both sides by T. Divide both sides by T. So you can now see that this is V, and of course this is omega. And then we end up having V is equal to what? Omega R. Okay, that may be another way. Of course, remember that if you also divide both sides by T, then you will get the relationship between linear acceleration and angular acceleration. That's A is equal to angular acceleration times R. The same thing. Someone may be asking, how do we prove that theta is equal to S over R? So let's go ahead and prove it. Now, let's still draw our circular path. We have our circle here, all right? The same thing, this is the center. Then we have our object A, B, and then this is the theta, all right? And this is our S, okay? If we take the ratio just like we did before, we are going to get that S all over 2 pi R, that's the circumference, S is part of the circumference, is equal to theta all over 360 degrees, right? Okay, so what do we do now? If we recognize that 360 degrees is equal to 2 pi rad, just plug that in, and then you will have that S over 2 pi R is equal to theta. Then instead of writing 360 degrees, we're going to write 2 pi rad. Okay, so that 2 pi can take care of 2 pi, and then we'll be left with what? We'll be left with S over R is equal to theta all over 1 rad. If you tidy this up, you will still get the same thing. Theta is equal to S over R, okay, in rad. So that's it. Next question. 3. The value of centripetal acceleration is given by the expression this, where V is the speed and R is the radius of the path. Show that this expression is dimensionally correct. Okay, so what do we know about the unit or the dimension of acceleration? We know that acceleration has meters per second squared as its base unit. All right, and of course the dimension will be for length. This will be capital L times capital T minus 2. This is the dimension. Hope I'm correct. Yes. Okay, so if we evaluate this and we get the same unit and dimension, it therefore means that the expression is dimensionally correct. So let's evaluate V squared over R and see. The unit of V here is meters per second. So let's take the square of it. All over R. The unit of R is meters. Okay. If we work this out, we are going to get that meters squared per second squared all over meters. Then this takes care of one of the m's in the numerator, and then we end up having that meters per second squared, which will eventually give us the same dimension, that is L, capital L, times capital T minus 2. So it is dimensionally correct. All right, two objects A and B move along circular paths of different radii, but with the same angular speed omega and from the same fixed point. If the radius of A is twice that of B, its linear or tangential velocity V will as well be twice that of B, true or false? The answer is true. It's true. Alright, so let's prove that it is true. So here I have a circular path, and here is the center, and I have another circular path. So this object is here, and this object is here, and the distance from here to here is r, and the distance from here to where this object is 2r, or let me use r here and use r over 2 here. Okay, I believe you can understand. Okay, so from the formula V is equal to omega r, we can see that this is constant, just like saying V is proportional to r, with angular speed being constant. Of course, the two of them, even the question captured it, that the two of them have the same angular speed. Of course, that's how it should be, but the linear speed should be different for the two of them because the radius is different for the two of them. All right, so if we establish our constant, V is proportional to r, and then V is equal to kr, where k is omega. So I can say V all over r. I'll put 1 here, equals, and here I have V2 all over r2. Okay, now r1 is r, and r2 is r over 2. So plug that in, and then let's see what we are going to get. Here we have that V1 still remains the same, all over R1 is R, is equal to V2 all over R2, in this case is R over 2. And this will give us V1 all over R is equal to V2 times 2. I want to take this 2 up, right? All over R. Okay, and so this takes care of this, and we can now see that V1 is equal to 2 times V2. Hence, true. The question is true. The correct option is true, rather. All right, the next one. The period t of a body undergoing circular motion is inversely proportional to its linear speed or velocity. True or false? It's true. It's true. It's true. Okay. Now, how true is it? Recall that V is equal to omega r. But again, I know that omega is equal to 2 pi all over t. All right. Now, we had considered this before. Please, if you skipped any of the sessions, please go back and watch them. So omega is equal to 2 pi all over t. If I plug this in here, I'm going to get that V is equal to 2 pi r all over the period. So I can now see from here that period and V are inversely proportional. So if I increase the period, let's say from 2 seconds to 5 seconds, what then happens to the speed? The speed will do what? The speed will drop. So imagine that we are, doing an experiment that has to do with a simple pendulum. The simple pendulum, the speed of the pendulum bob, of course, will reduce. Is that okay? All right. So from here, we can see that the correct option is true. The two of them are inversely proportional. Okay, the next question. The Earth moving about its axis is an example of circular motion. True or false? Is false. Is false. All right, because you have, this is the Earth, for instance, and this is the axis of rotation, and let's imagine that here is the center, the equator. All right, this is rotating like this. Okay, the center of rotation, the central position, the axis of rotation is within the body. All right. Wherever for a body performing circular motion, remember we did say previously that the center has to be outside of the body. So you have this body here, then moving around this central position. But in this case, the center or the fixed point, all right, is within the body. Therefore, this is rotational motion, not circular motion. All right. An object undergoing uniform circular motion has constant / uniform acceleration. True or false? Okay, the answer is true. Now, what we call centripetal acceleration, what we call centripetal acceleration is actually a net constant acceleration. Okay, and of course, centripetal force is a net constant force. Take note of that. So the correct option here is true. All right.